In this video, we're going to be talking about galvanometer as an ammeter. Now, this simply means we are converting a galvanometer to an ammeter, or we want to make a galvanometer work in the way that an ammeter does. First things first, what's the difference between a galvanometer and ammeter? Now, a galvanometer measures current, an ammeter measures current as well, but the main difference is that an ammeter measures great amounts of current, while a galvanometer is only allowed to measure tiny amounts of current. Now, these two work based on generally the same principle due to the fact that current moving in a conductor produces a magnetic field. Okay, now I have a galvanometer on the board. Okay, but before I show you how we convert a galvanometer into an ammeter, we need to know how an ammeter works generally. Now, for an ideal ammeter, it is simply an ammeter that is assumed to have a very small amount of resistance, that is the tiniest amount of resistance available for that ammeter. Or some persons or some books you find will tell you that it has negligible resistance, but in research we do know that it has an internal resistance. Okay, so an ammeter or an ideal ammeter is an ammeter that has a very small amount of resistance. Okay, but the truth is that for a real ammeter, when you find a real ammeter, there is some finite amount of resistance you find. Okay, but for an ideal, okay, that is a generally accepted one, is one that has what now a very small amount of resistance. Okay, now to convert a galvanometer into an ammeter, we need to make the resistance of a galvanometer, okay, I'm going to write the resistance of the galvanometer Rg, okay, so small, that is the net resistance in this circuit, so small so that it cannot register great amounts of current, and then it becomes what now, an ammeter. That is what we simply want to do. Now, to do that, you have to recall that when we talk about resistors in series and in parallel, okay, for resistors that are connected in series, the final or the net resistance becomes greatly increased, okay, and then for resistors that are connected in parallel, the net resistance becomes greatly what now, reduced, and the net resistance for that parallel connection is always less than the individual what now resistors that are connected in parallel. So if we can connect a very small amount of resistance to this galvanometer in parallel, the net resistance will be smaller than this one, which means if the net resistance is so small, okay, that is almost negligible, we can now what now, use the galvanometer to measure what now, current, in a way that an ammeter does. Okay, now we'll assume that the current that is coming into the circuit is I, the one that goes to the galvanometer is Ig, and the one that comes into the resistor is what now, Is. I'll tell you why I'm calling it Is. This is because the resistor we are connected in parallel to this guy is called a shunt. Okay, the kind of resistor we connect in parallel to this guy is a shunt. Not like there is a special kind of resistor, but the name is just called a shunt. Okay, so a shunt is that resistor that will connect in parallel to the galvanometer, and it has a resistance which we are going to call Rs. Okay, now from here we can now apply Ohm's law and Kirchhoff's law to solve for it and find the current or the resistance, or the amount of resistance to get the current in which you are looking for. Okay, now since they are connected in parallel, we do know that the voltage across the shunt is going to equal the voltage across the galvanometer, of which we know that Vs is simply Is times Rs, and Vg is simply Ig times Rg, that is current times resistance, current times resistance. Now Rs is what we're looking for, so we might want to make Rs the subject. That means Rs is going to equal Ig times Rg divided by Is. That is what we are going to get, okay? Ig times Rg divided by Is. But we can as well work with this or manipulate this now by applying the KCL rule, that is the Kirchhoff's current law. Okay, the current that is entering this junction is equal to the current going out and the current going out here, which means that from KVL, I'm going to write from KCL rather, from KCL we notice that I is equal to Ig plus Is. Now this rule is gotten from Kirchhoff's law, but if you've not watched our video on Kirchhoff's law, probably you are just studying this first. Okay, it's very easy. The current that is coming in is equal to the current that is going here plus current that's going in. That is what KCL talks about. Okay, So from here, we might want to make substitutions for Ig or Rs. So we can as well say that Ig is equal to I minus Rs. Now, if we substitute into this equation, we are going to get Rs is equal to, substituting for Ig, we are going to get I minus Ig, okay, times Rg divided by Rs, where I is the current that is coming into the circuit, or we can simply write this as Rs is equal to, leaving the up untouched, we get Ig times Rg divided by, making Is the subject instead, we get I minus Ig. We get I minus Ig. Okay, so here are the formulas that have been used to solve problems like this. Now, these are not formulas that you might have to cram. All you have to do is understand the concept. Okay, we have to connect a low resistance shunt in parallel to the galvanometer in order for us to convert it into an ammeter. Okay, so here is simply the principle behind how an ammeter is being created, or rather how a galvanometer is being converted into an ammeter. Okay, now in our next video we'll be talking about conversion of a galvanometer into a voltmeter, that is by using a multiplier. Okay, so do well to click on the notification bell so that when new videos have been uploaded, you'll be one of the first few persons that will get notified about it. Okay, the concepts that we just dealt with right here is quite easy. You might want to go over the video 1 or 2 more times to get a great understanding on how conversion of galvanometer to an ammeter is being done. So see you in the next video. Stay tuned.